where we are. Note that the DSP, this is a vector. And if I write k as a subscript, it means I want to subscript it at bin k. So k is the bin number. So I'll even write that k equals 0, 1, up to n minus 1. And that's our bin number. And we know how to convert that frequency, right? So what's the formula for omegas of k? What is the k radian frequency in this?
This is a question that is open to you guys. How do you calculate the digital frequency from the bin number?
2 pi kf.
Say it louder.
2 pi kf.
We've got a 2 pi kf.
2 pi k times what?
The frequency.
What? The frequency
Yeah.
rates?
Where f is the frequency.
Where f is in what units?
Hertz.
Well, where's the sampling rate? You need a
Per
sampling rate.
samples. It's not.
Oh yeah, yeah,
It's not
yeah.
hertz.
Yeah, samples per second.
No.
Right.
It's just in samples. It's per
Oh,
samples.
samples, yeah.
So, okay, so 2 pi k something. What's,
Over n.
Over n.
yeah, so there's going to be an f in here of some kind. And, you know, in n, so there's going to be a division by n, for sure.
Mm-hmm.
And then, what f do I put here?
S.
What f is that?
We're hearing f sub s here. So the sampling rate.
Yeah, yeah. And so we can also write that as k times 2 pi. So you can think of the sampling rate as having been divided into capital. Remember this picture of the unit circle, where you just lay down as many. You divide the circle into as many sections as you have points, and that gives you the generators for those sinusoids, those frequencies. So, so this is 0 or fs. So this is the point e to the 0 or e to the j 2 pi equal 1, right?
Or to generalize that j 2 pi k, because it does keep going around and around.
Yeah. So, for example, this one is e to the j omega 1 t. That's how I like to write it. So e to the j omega 2 t is here, and so on and around. And then taking successively higher powers of that, we'll multiply the sampling interval by a counter. That'll generate our time axis, and then the whole expression will generate our sinusoid, our sampled complex sinusoid. Another way I like to write this actually is omega sub k t. So if you just associate omega with t, so just think in terms of omega t, omega capital T, then that's your normalized frequency axis. And so that would then be 2 pi k over n. And I just think that one's pure. And so it's in the range of minus pi to pi. And we can do it half over. And sometimes you'll see people use different notation for this, like since it's normalized. I've seen notation like omega hat, or you can use a different variable. It's your normalized radiant frequency. In minus pi and pi. And this is what you see most often in single classical conductor. Okay, so let's get another page going here. I have that. We don't need to see anything there. Let's just go to the next page and start over. E of t. So x of k, the kth element of this vector, x of k. Is that on the screen? Yeah.
Yes, you're good.
So the way we're thinking about this now is as an inner product of the signal f with s sub k, where x is our input signal. So I could write x as, we say x is, mathematically we want to use column vectors. So we'll have x of 0, x1, down to xn minus 1. In MATLAB, we want to use row vectors, but mathematically it's more common to use column vectors for, anytime you have a vector, it's a column by default. And if it's a row vector, you think of it as a transposed vector. And since these are all complex in general, it's going to be Hermitian transpose, complex conjugate.
So this inner product, we're taking the inner product between the signal x and this signal s sub k. Can anyone tell me what s sub k is?
Sinusoid for at frequency k.
Yes? It's a complex exponential. So it's not just the real part of a sinusoid or the imaginary part, it's the entire complex exponential. Good.
So who can tell me the formula for the nth component of s of k? What's the formula that I can use to fill in this vector? Some formula of n for n equals 0 to n minus 1.
And God, I'm going to say it's e to the j times something.
It's e to the j something, yeah.
Yeah, okay, anybody want to know?
What do we got? What's the something?
So we're going to need an n up there.
We're going to need an n.
Yeah. I think I have an n here.
We're going to need a k, right?
Yeah, for the frequency.
We need a k for frequency, so we have the nk.
Okay.
What else are we missing?
Yeah. Sampling rate? Or,
Oh, not quite the sampling rate.
no.
We could use the sampling rate.
Okay, if you want to use the sampling rate, you can.
I don't need
Introduce the sampling rate, and then we'll have to introduce something to cancel it, because the ultimate form is going to be pure like this. If we can introduce the sampling rate, then we have to cancel
Let's not do that. So if you refer to the DFT up on the board, we have the 2 pi, and then we also divide by n. Can anyone provide an explanation for why we do either of those things? So why do you typically use 2 pi?
Convert between radians and hertz.
And so the quantity n, little n times k over big N is talking about it going around the circle, right? K is going to be the rate that it moves around the circle. It corresponds exactly to the frequency of the sinusoid. And little n over big N you can think of as the fraction of the way around. And so when we have that 2 pi there, it's because we're converting to radians. So exactly what this guy here means is that you're, as was mentioned, you're taking the inner product of the signal and the sinusoid s sub k to get this thing, x sub k. This is a projection of x onto s sub k, and it gives you this quantity that is roughly the amount of x that is of frequency s sub k. You're projecting this onto this. And I've got a demo for projections later that should make that a little bit clearer. Questions on that? Yes, thank you.
So what is the x part of your signal if your sinusoid is L and S?
The x part is going to be the amplitude of that sinusoid. So by projecting your arbitrary signal x onto a sinusoid of a very specific frequency, we're getting this quantity here that is the amount of that signal that we have expressed as the amplitude, and not just a real amplitude, a complex amplitude. This number is going to encompass both the magnitude, and the phase. Questions? Is that clear?
So that x sub k is like one bin in our final DFT vector.
Exactly.
Awesome.
I think we're ready to proceed.
Okay. So on the previous page, we calculated omega sub k. So let's say we want to take this one, and maybe even this one is better because it's normalized. So 2 pi k over n we can think of as normalized frequency, normalized radiant frequency. Right? It's omega t. Let me go ahead and write that. It's omega k times capital T. That's the definition of it. It's normalized radiant frequency. It's in minus pi to pi. So let's see if we can use that over here. 2 pi k over n. Remember, 2 pi k over n is our normalized frequency. It's one of the DFT frequencies. So we have 2 pi k over n here, and it's just multiplied by k. So if I have the normalized frequency here, then 2 pi k over n is the normalized frequency. All I need now is just n. So that shows you how to generate the k complex sinusoid in terms of the normalized radiant frequency. It's just e to the j omega hat n. And if I want to get rid of the hat, then I have t sub n, or I have little n big T, which is the same. So remember, t sub n equals n t. If we wanted to write it in those terms, we could. If we wanted to not be a normalized frequency. The normalized frequency is very commonly used.
Could you go over that one more time and just elaborate a little bit more on that? Because I don't think it's especially clear why you would write it in that different way with the NT.
Okay, let's see. Let's go down here. No, I'll go with this way. So what we had was, we have that S of k of n is equal to, by definition, e to the j 2 pi nk over n. So that's the completely pure form of it. But we also noticed that, omega sub k t, which we're defining as omega hat sub k, that's our normalized frequency, is equal to 2 pi k over n. So it's a pure thing. And so that means that we can plug this in up here and write the complex sinusoid as e to the j 2 pi k over n is all part of the normalized frequency. And then all this stuff is in n. But if we want our time to be in physical units, then we can get rid of the normalization. So we can say that, we can expand omega hat as omega t times n. And then we can associate the n with the t and call it e to the j omega sub k. And nt is t sub n. It's the nth sampling interval. So that gets us back to the original notation that I like the most, because it's the most physical. It looks like the continuous time case evaluated at t equals t sub n and omega equals k. In other words, we're just sampling the normal continuous time, continuous frequency Fourier transform frequency. And it's good to have that kind of unified view of frequency.
1 second, Julius. We have a question. Yes.
Where did the big T come from? Because I don't see it in the e to the j 2 pi n k over n. I understand that equation, but I don't really understand where the big T came from, so we can use the normalized time.
Did you catch that question, Julius?
Well, the big T is over here.
Yeah. I mean, like, how did we sub in the normalized radiant frequency without that big T in the exponent there?
Well, the way we got there was from here, where we had omega k is 2 pi k S of S over capital N, and then we basically multiplied this equation by capital T.
Okay.
And that gave us this line. So here we get normalized frequency, omega ck T.
Pause. If for anyone who doesn't see why that gets us from this line to this line, it's because T is equal to 1 over Fs. This is your sampling rate. This is your sampling period, the time in between which samples are taken.
So it's getting us back into the actual time,
Exactly. This.
like, instead of talking about it in terms of samples.
Can you pull the page up a little bit? This right here shows us how to express these frequencies in terms of time. So if you remember, and I don't expect you to remember, we talked about the continuous Fourier transform probably for a fraction of a second, where you see this, and this are the same. What you're doing with the discrete transform is you're basically sampling the time. This just shows it in these sampled time units. Questions?
Very cool.
What is T sub n?
We've got a cool T sub n is the nth sampling time or nth sampling interval. So remember, if you've got your time axis here and you take samples here, 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 these are your samples 1, 2, 3, 4. T sub n corresponds to the time at which the nth sample was taken. So this occurs at T sub 4, which is going to be the fourth sample divided by the sampling rate, or the fourth sample times T, which gives you, if this is time 0, it gives you this time in seconds.
Cool. So it's like the same equation, but now we're just expressing the time instead of in samples in like time in seconds.
In natural units, yes.
And T is 1 over the sampling rate?
Capital T is 1 over the sampling rate, and capital T is the sampling period, the time in between which samples are taken.
The capital T is the sampling period or the rate?
Capital T is the sampling period. 1 over capital T is the sampling rate. Remember, you'll always see that inverse relationship between time and frequency. Time is 1 over frequency. Frequency is 1 over time.
So just to reiterate this a little bit, we're working with complex sinusoids that are sampled in time and sampled in frequency, and then we can expand those out. So the K radian frequency is K. Remember, you take the integer K and multiply it by 2 pi divided by n. That's the piece of the circle that you have. And then the circle itself represents that's the best hertz all the way around. So this is just a way of writing omega sub k. And then T sub n is just nt. But then T and S of S cancel in this expression. So try to draw the cancel. Thought that was going to be a red pen. Look how nice and red that pen is. You'd think, oh man, that's going to be That's not true. So those cancel and give us a pure, nothing but pure numbers, which they must be. You really must have a pure number in an exponent. You can't raise something to the number, some number of seconds. What does that mean? So, so those cancel, go away, and what we're left, the way it's normally written is 2 pi n over capital N. That's kind of the standard layout of what's left in most books.
Cool. I'm satisfied.
Good. I think they're happy.
Okay. All right. So now, what we're doing is understanding this as a projection. So let me go back to the projection view. So we have d of t. It's a vector that's obtained by projecting our signal x, viewed as a vector, onto a vector which is the kth d of t complex sinusoid. And we've got all the formulas figured out here. And then I've written down here the sort of geometric interpretation of that. And Chet's going to go over that in MATLAB and on the screen a little bit later. So this is an n-dimensional space, right? So I'm only plotting it for n equals 2 here. So every sample of your signal is just a coordinate, and your whole signal is just one point in this n-dimensional space. And then, because we want to think of it as a vector, then we draw an arrow from the origin of the space.
So just to reiterate something, this is not your DFT. It's not your entire DFT. This is a single bin of your DFT. In order to get the entire DFT, you need to evaluate this at every x sub k, which is going to take you from DC up to Nyquist, and also your negative frequencies. And the number of bins that you'll end up with is the number of time samples that you started with. So if you have a signal of length big N, you're going to have big N bins in your FFT or in your DFT, which exactly corresponds to this big N right there. Is that notion clear, that this is just one part of your DFT? You do this many times. It's the exact same formula with different Ks. Okay. Continue.
Okay, so this is the geometric interpretation that we're focusing on here. And as I mentioned before, it's a very, very general way of decomposing signals into sums of other signals. It's called the Hilbert space approach. It's Hilbert space modeling.
Don't go down that road yet.
I'm not going down the road, but I want you to know the name. I want you to understand the term.
Okay.
The setting that we're in. It's just a name. It's just a name for the world that we're in. It's geometric signal modeling. There are a lot of ways to talk about it. But this is what it is.
You should not concern yourself with Hilbert
using
spaces.
A set of signals. Let's go ahead and say what it is. S of k is the k basis signal, or vector. Yeah, let me say vector, since that's a more common term. And it's for the complex space we're in, which is Cn. And that's the set of all length n complex sequences.
You're off the page.
Okay. Now, I'm not going to talk about Hilbert spaces other than to say that that's the proper name for the setting that we're in.
You're still off the page.
Really? Oh.
Well, now you're almost actually off the page.
Let's see, what's going on here? Well, I'm only trying to show you the bottom, right? I don't need the top on the page.
Okay.
I know the top can't be on the page. We're scrolling. Let me go on to the next page. All right, so yeah, let's just start up here. It's easy to restate what we need. So this should be on the page nicely. X of k is equal, which is by definition the d of t bin k of x. And let's go ahead and so x is the whole signal, right? And you can put an underline under it when you want to really emphasize it's a vector. And I've got the k subscript here to indicate that I'm only looking at the kth bin. And so then the definition here is the inner product of the signal x with the kth basis sinusoid. And so we do that for all k. And that gives us an invertible set of projections. So if I want to complete the n equals 2 case, then what I can do is look at S0. S0 is the point 1, 1. In other words, bin 0 is always DC. So your 0 DFT sinusoid is always going to be 1, 1, 1, 1, 1, 1, 1 for the space. So
Pause.
now what is S1?
Pause. Can anyone explain what we're doing right now? What it means to take a DFT with n equals 2?
Just 2 samples only.
And how many frequencies are we going to get back out?
Just 2.
What are those frequencies? This is your bonus question.
Well, if we take that,
Close. Those are the same frequency.
Zero.
0 and pi. So you're going to get there are two frequencies out of this, your 0 and your pi. And your 0 frequency, of course, if this is your 0, is going to look like this. And every sample, let's draw this as samples, is going to look like this. Your pi frequency is going to be alternating. One sample above, one sample below. Of course, you're only going to be looking at the first two. So if you have some x that's 2 samples long that looks like this, or anything, let's say it looks like that. You're going to decompose this into some scaling of this and some scaling of this. So if you want to calculate this, you're going to project this onto a sinusoid of frequency 0. And what this value is going to turn out to be, it's going to be the average of those 2 points. And for this, you should be able to see that centered around this average, you have something that looks like that, where those are 2 samples, one above, one below, and also this distance here and this distance here are going to be the same. So what you should try and do is convince yourself that for any arrangement of 2 samples, any different 2 samples of any height, you can decompose them into this, the DC part, and the Nyquist part, where the DC part is going to be the average, and this is going to be the deviation around that average. That is not a happy look. Should I say that again in a better way, or did I just catch you in a weird look?
No, I was lost from a point before all that.
Yeah.
Okay.
What is the whole diagram that you're trying to?
This is just time domain. All across the board, this is time domain. This is a signal. Any signal, 2 samples, I don't care what they are.
So it's not the real. It's the whole signal, including the X part and the S part.
This is just the X. This is your signal. You haven't done any analysis on it. You just took a measurement of 2 points. That's your signal. You don't even know you're taking it to frequency space yet. When you go to take it to frequency space, you're going to do that inner product with 2 different S sub k's, an S sub 0 and an S sub 1. This is your S sub 0. It's a DC signal, a sinusoid of frequency 0. And this is your S sub 1. In this case, 1 corresponds to Nyquist. Show of hands, who's with me so far?
What do you mean by, what does that have to do with Nyquist?
Yeah.
Like you're just throwing that word around.
But that's
Any signal that's a sinusoid at Nyquist is always going to look like 1 sample above, 1 below, 1 above, 1 below, 1 above, 1 below.
Okay, that's helpful.
because that's like the
Because
lowest sampling rate we could have to measure that
Okay,
signal.
yeah,
Mhm.
that makes sense. Yeah.
that's what it means to sample at Nyquist. We've got a signal that looks like this. With only 2 samples, your Nyquist is going to look like that.
So if you have n samples, then n would be the bucket that would look like Nyquist, right?
Yes.
Yeah.
S sub n would look like Nyquist.
Yeah, the last bucket of your DFT is going to be the Nyquist frequency.
Well, it's a tricky thing because they come to Nyquist and they go all the way back around for your n over n, right?
Yeah, it's just that this is a special case, so we don't actually see any points where we go past.
Yeah, you don't see anything else. In this case, you only have this point and this point.
Right. So S
Normally,
sub
Nyquist is going to be in the middle.
Okay. But S sub capital N would look like that.
S sub capital N. I don't think that's true. Julius,
What?
for your bin that corresponds to Nyquist, that's not always capital N, right? It is in the two-point case, but it's not usually. Can you verify that?
Yeah, normally, let's say we do n equals 8, then the way you lay it down is you always have a sample of DC, All right, so that's DC. And then for an even length, you will get a sample at Nyquist. For odd length, you will not. And also, let me just sort of give a historical note. The Nyquist rate is historically the sampling rate. So, but a lot of people talk about half the sampling rate as Nyquist, and that's just setting up a confusion and conflicting history. So what I like to do is call this half the sampling rate point Nyquist limit, and that way we can use Nyquist on both of those frequencies. So the actual Nyquist rate is the sampling rate, which is the same as DC, right? Because if you sample the sine wave at the sampling rate, it looks just like DC. You're sampling at the same phase every cycle.
I think this is going to cause confusion. I think we should pick something to call Nyquist and leave it.
And let's say, and I think I can resolve this, and I say we'll call it Nyquist limit. And if you say Nyquist for short, it's ambiguous whether you mean half the sampling rate or the full sampling rate.
Then I'm going to call it half the sampling rate.
Yeah, that'll be good. That'll be good. Yeah, I just want to avoid confusion because those two names are out there. But the earlier historical name is the one that I'm sticking to, and I think that we have the right to do that. Also, good books like Oppenheim and Schaefer will not get it wrong.
Okay. Well, to continue with that explanation, then this corresponds to your half the sampling rate frequency. The fastest frequency at which you can sample a sinusoid is the frequency that gets you a point above, a point below, a point above, point below. If you sample any slower than that, you're not going to capture that information and you're going to misrepresent the frequency. This is just aliasing. This is last week's stuff or 2 weeks ago stuff. The point I was trying to make with this is that you can represent any 2 points as a sum of scaling of these two signals, where you have +1, +1, +1, -1.
And that generalizes out because you can describe any number of samples as within DFT.
Yes. So when you have an n-length sample, you'll be able to represent that signal as a sum of all of those, where you have not just the DC and not just the alternating case, but all the sinusoids that are represented in between.
Yeah.
But it's good just to get your head around this one first. So you'll be able to prove that the DC component is going to be the average of those 2 points wherever they may be. If they're up here and up here, the average of them is going to be 0. And it should be clear that you can represent this completely with this. When your signal looks like this, you can represent it completely with this, and you don't need this. Any other mixing of these two things, and you can get any other arbitrary signal. Is that much clear? That we can scale these two things and add them together, and we can get any 2 sample signal. Questions?
So those are your basis vectors? And
Exactly. These are the basis vectors. Yes, you're taking a linear combination of these, and you can create any 2 sample signal for this.
There's just more things happening.
Is that clear?
Yeah, that totally makes sense. And you could say that in real person words by saying any sound can be described by the sum of n sinusoids of different frequencies.
That's the continuous case.
Yeah.
I mean, what we're doing here is we're reconstructing the Fourier series. So I guess Julius is kind of writing in math what I am doing in pictures for those of you that like the math version of this. I think the picture version is probably clearer. That's the 2 sample case for this. Julius Ross is giving you funny looks.
I'm just writing out what you're saying.
Yeah. Is this picture clear?
Yes.
Come visit me if this picture is not clear. So I think I probably just pulled the carpet out from under your